So, what we are going to do is, so here is a linear plant and here is a nonlinearity, and we are assuming that this nonlinearity is in the K1 infinity sector. Okay. And we would like to know that when you do this feedback connection, what are the linear plants? Okay, so the question we would ask is the following: how to characterize all linear plants which, when connected to nonlinearity in the K1 infinity sector, results in asymptotic stability. Okay. So, now let me call the input to the linear plant u and the output y, and let me call the input to the nonlinearity psi and the output phi. Okay. Then of course, by the feedback connection, then you know u is equal to minus phi. Okay. And you also know that the transfer function g is really y by u, but that is the same as psi by minus phi. Okay. Now, so earlier we saw that given this nonlinearity with input psi, output phi, such that this nonlinearity belongs to the K1 infinity sector, you can get a new nonlinearity. So, let me call it NL1, such that it has the same input, but now the output is phi tilde, such that this NL1 is really, it belongs to the 0 infinity sector. Now, how does one get this NL1 from this NL? We just saw earlier that one way to get this NL1 from this NL is by using this feed forward, where you take this gain K1 and feed it there, and therefore, now what you have will be phi tilde. Now, you originally had a G of S here, which you had interconnected with this NL. Okay. So, what I am trying to say is that you had this G S interconnected to the nonlinearity NL. Okay. And we call this u, we call this y, we call this psi, we call this phi. Okay. Now, one could modify this transfer function g of s into some new transfer function g1 of s, such that this g1 of s will take this modified input, but give the same output as the original g of s. So, what we are trying to say is that we modify this g of s in some way, such that it takes this u tilde as the input rather than the earlier u as the output, but gives the same output as g of s would give for u. Then we can calculate what this g1 of s would be, because this g1 of s, g1, the transfer function g1 of s is given by y divided by u tilde, but this is the same as saying xi divided by because y is equal to psi, and u tilde is equal to phi tilde minus phi tilde. But this minus phi tilde we know is the same as psi, this minus phi tilde is the same as minus phi. So, we had taken this phi tilde to be phi minus k 1 psi. So, I am just substituting for phi tilde. So, I have minus phi plus k 1 psi. Now, if you remember in the last slide I had written that the original transfer function g is really psi by minus phi. So, dividing by minus phi in the numerator and the denominator, we get this g 1 is really the original g upon 1 plus k 1 g. Okay. So, what we are trying to say is the following. Okay. So, what we are trying to say is the following. So, if you had a nonlinearity psi phi and you had this g of s, okay, then this interconnection is exactly the same as the following interconnection, where you have this nonlinearity, the same nonlinearity at the before. You keep the input to the nonlinearity exactly the same, but for the output what you do is you put a k 1 here, okay. So, you fed forward this k 1 psi, and so now you have this new input phi tilde. Now, this new input phi tilde you are feeding back, then the resulting transfer function that you would have here, which one called g 1 of s, as we just derived in the last slide, would be g of s upon 1 plus k 1 g of s, but that is the same as saying you have g of s and then you have 1 plus k 1 g of s. What that means is you have this feedback structure g of s with fed back with k 1 s, okay, and this resulting system. So, when you put g s with this nonlinearity, and this nonlinearity is in the k 1 infinity sector, and you have this nonlinearity. Now, you can convert this nonlinearity into something in the passive, that means, you can convert it into something in the 0 infinity sector by doing this feed forward. So, you have done a feed forward, and what have you done? You have forwarded the input to the output by this loop. So, along with the nonlinearity you have given a feed forward, but when you do this feed forward on this loop, on the open loop, what you do is you give a feedback with the same k 1 on the original plant that you had, and then this resulting plant along with this new nonlinearity. So, the new nonlinearity is what is inside this dotted box that I am putting, along with this new linear plant, which is what is there in the dotted box there. These two, this combination is exactly the same as this combination. Okay. And now, if this combination is exactly the same, now by using this feed forward, what we had done is this nonlinearity in the k 1 infinity sector, you had converted it into a nonlinearity in the 0 infinity sector. Therefore, you know that for anything in the 0 infinity sector, making use of the positive real lemma and the results about passive systems and so on, this resulting system here, if this is strictly positive real and stable, then that along with this resulting system is asymptotically stable. But that's, since this system is equivalent to this system, that's the same as saying that this system is asymptotically stable. Okay. Therefore, for a nonlinearity in the K1 infinity sector, given a GS, that GS with that nonlinearity in a closed loop system, this would result in asymptotic stability if, when you modify G to this thing, that means when you modify G to G1, where G1 looks like this, GS upon 1 plus K1 GS, and if this is strictly positive real and stable, then the original system is going to be asymptotically stable. So, I hope this is clear. So, what you are really doing is you are doing some sort of a loop transformation. Yeah. So, what you did is on the nonlinearity, you gave a feed forward loop, and as a result on the linear plant you give a feedback loop. Both these loops have the same gain. So, there is a feed forward loop with negative gain. Here you have a feedback loop with a negative feedback. Now, as a result, this modified linear plant along with this modified nonlinearity, they both together, now you invoke the positive real lemma or the Kalman-Yakubovich lemma, whichever one is applicable, and then you can talk about the stability of that resulting system, and this resulting system is exactly equivalent to this system. So, therefore, you can say something about all the transfer functions which, when interconnected to a nonlinearity in this particular sector, will give asymptotic stability. Okay. So, what is the result? The result is that if you take any plant and you do this transformation of the plant, this transformation of the plant should result in this new plant G1 of S being strictly positive real and stable. And if that is true, then the original plant G of S with this nonlinearity in the K1 infinity sector is going to give you stability. Okay. Now, that was one special case where you took a nonlinearity in the K1 infinity sector. Now, one could also think of taking a nonlinearity in the 0 K2 sector. So, if you take a nonlinearity in the 0 K2 sector, so what will its characteristics look like? So, if I call this psi the input and this the output phi, and I draw this line which has slope K2. Since the nonlinearity lies in the 0 K2 sector, that means nonlinearity is something like this. Okay. Or in other words, phi by psi is less than equal to 0. 0 is less than equal to phi by psi, which is less than equal to K2. Okay. Now, if you have nonlinearity of this kind, then this particular inequality I could rewrite this in the following way. You see, if I take K2 psi minus phi, so suppose I take some point psi. So, this point here is K2 psi and the corresponding phi is this. So, this quantity here is positive, and for this particular case psi was positive. Yeah. Now, similarly, if I take psi to be negative, I get K2 psi to be here and I get phi to be here. So, K2 psi minus phi, this is negative when psi is negative. But more importantly, K2 psi minus phi this quantity here is positive. So, I could write the following. You see, when psi is positive, phi, the corresponding phi is also positive, and here when psi is negative, the corresponding phi is also negative. So, I could write the following down: k2 psi minus phi transpose multiplying phi, the output. When this is positive, this is positive, and when this is negative, this quantity is negative, this quantity is negative. So, this product is greater than or equal to 0. And so, what I have really done is I have looked at this nonlinearity, and I have looked at certain quadratic inequality which gets satisfied by any nonlinearity which lies in that sector. And now, what I am going to do is I am going to use this this particular quadratic relation to modify my original nonlinearity in such a way that now it becomes a nonlinearity in the 0 infinity sector. Okay. So, how do I do that? I do something very similar to what I did the last time. So, here is the nonlinearity, here let me assume is the input, and here is the output phi. Okay. Now, what I am going to do, the last time what we did was we kept the input the same and we modified the output. This time round, what I am going to do is I am going to keep the output the same, but I am going to modify the input. So, the new input psi tilde is going to be equal to k2 psi minus phi. Okay. How do I do this? Well, what I could do is I could take this nonlinearity, the output is still going to be the same phi, but the input, the new input is going to be this psi tilde. But let me do the following. Let me put a gain here which is k2 inverse. So, now if I give k2 psi as the input here, then because of this k2 inverse I will get psi here, and then I have the original nonlinearity. So, what I am trying to do is I should get psi here such that I have the original nonlinearity. So, the original nonlinearity I am multiplying, before you reach the nonlinearity I am multiplying the input by k2 inverse. Okay. And so, now I would use this output, yeah, and I feed this back, right. So, now if I am to get psi here, what I should get here is k2 times psi, and so what I should get here should be k2 psi plus phi. So, if out here, so I want k2 psi minus phi here, because that is what I want here, and so what I will do is I will feed this back, use a positive feedback. So, if I do k2 psi minus phi here, if I have k2 psi minus phi here and I am feeding back this phi will cancel out that phi, and I will have k2 psi here, and then k2 inverse will give me psi here. So, I have the original nonlinearity modified in this particular way should give me a nonlinearity like this. And this nonlinearity, so now if I box this off, this new nonlinearity has the same output as the original nonlinearity, but as the input it has k2 psi minus phi. Okay. So, it looks like I am out of time. So, we will continue whatever we are doing in the next lecture.